Lesson 84 is logarithmic differentiation. So it is yet another method to put in your toolbox, so to speak, of how we can differentiate. Now, and I was going to write up here that we kind of already talked before I started the recording that, yes, it can be used instead of product and quotient rules. As you look, today, a lot of things are good to be done with quotient rule. But I don't know about you guys, but example 3, doing that with product and quotient rule would be disastrous. Okay, so I was going to put a little starred comment up here that this can be used in place of product and quotient rules. So that is one little side comment I wanted to get listed here and get noted. Just, that's basically, it's another method to take derivatives. Well, I don't know about you, but product and quotient would be intimidating here. Okay? And then the other thing, we're talking about using logs, obviously, right? You've seen the name, you don't know how it works. But we're talking about using logs. So logarithmic differentiation, what do you guys remember about the inside of a log? Officially, the inside of a log can never be negative. Now, so what I'm going to say here is that we want to temporarily restrict, just as we're working through this, basically think, okay, these are all going to be positive values for right now. Okay, so temporarily restrict the x values to represent positive values. And that's just because we're going to take the log of both sides. When we take logs, we're not supposed to have negatives there. Well, depending on what the x values would be, could be negative. So the other little side comment I was going to put here is temporarily restrict x values to represent positives. I'll just say it that way. Okay, so 2 little side notes before we get started. I just want to have those up there so you can remember. As we look at example 1, obviously they give us an equation. They ask us to find the derivative. With logarithmic differentiation, the first step is to take the log of both sides. Now, when I say take the log of both sides, technically, we could do log of any base. What is the log that has the easiest derivative associated with it? Even easier than log base 10.
Okay, yeah, right?
Natural log, right? So technically you could do log of any base, but we're going to do natural log. So my first step here is I'm going to write the natural log of both sides. So I'm going to start with the natural log of y equals the natural log of x squared over 3x plus 2 to the 4th. And as I said, there are lots of steps, lots of writing here. I probably should have skewed that over to the left a little bit, but now we're not going to take any derivatives yet. Okay, that's a couple steps in. First thing we did is we just took the log of each side. Now, think about your log rules. We have some log rules. Natural log of y is just going to carry down for right now. How can I rewrite the log of a quotient?
It's 2 logs minus each other, right?
Right. A log with division inside the log can be rewritten as 2 logs being subtracted. So I can rewrite this left as the natural log of x squared minus the natural log of 3x plus 2 to the 4th. So we're using our log rules here that you learned 2 years ago in Algebra 2. I think we would have maybe used them a little bit in pre-cal. That could have been something I skipped over, though, in time-wise.
we went over them this year too.
And we might have gone over them this year. Now, one thing I would do before we're getting close to being ready to take our derivative, so you want to use any product or quotient rule here that you can in terms of separating your logs. And then I also want to use the power rule for logs. Do you remember the power rule for logs?
So you can take the power and make it a coefficient, right?
Right. We're going to take the power and make it a coefficient because that will make, when we do the derivatives of these logs, that will give us easier values to work with. So it's still going to be the natural log of y. Natural log of x squared I can rewrite as 2 natural log of x minus natural log of 3x plus 2 to the fourth. Move that 4 out front, and it's natural log of 3x plus 2. Once you've separated the pieces, either the multiplier divided pieces, either by addition or subtraction, once you've used that power rule, now we are ready to take the derivative. Now, as we take the derivative, because we are going to be, technically we have x's and y's, if you will. There's only one y, but we technically have x's and y's. We're going to use our differentials. Anytime you take a derivative of an x term, you're going to tack on a dx. Anytime you take the derivative of a y, you're going to tack on dy. But you're taking the derivative of everything across the way. So what is the derivative of natural log of y?
1 over y.
Okay, so the derivative of natural log of y is 1 over y, and then I'm going to say times dy. What is the derivative of 2 natural log of x?
2 over x dx.
Okay, so the derivative of natural log of x is 1 over x, times the 2 that's there makes it 2 over x, and then since we're working with x's, we're going to say times dx. Minus, what's the derivative of 4 natural log of 3x plus 2?
Times dx, right? Because you have to chain rule everything.
It is going to have a dx.
Yeah, so, but would you have to do chain rule, so it'd end up being like 12?
Yes, there's going to be a chain rule also. So the derivative of natural log of 3x plus 2 is 1 over 3x plus 2 times the derivative of 3x plus 2, which is a 3. And what else do we have out front or on top? The original 4. So I just wrote it as 4 times 3, but realizing it is going to be a 12, like you suggested. And then, of course, times dx. Are we there?
Not yet.
Well, I mean, are we good at this point?
Yes.
You're caught up with me. You're okay with what I've said. Okay, so next thing I'm going to do is I'm going to kind of clean up that right side. Notice on the right side, and this is traditional, that all the terms are dx's, aren't they? So I'm going to kind of factor out that dx on the right, and I'll put it at the end. So my left is still going to be 1 over y dy. My right, I'm going to factor the dx out and put it at the end. So the other pieces are 2 over x minus 12 over 3x plus 2 in those parentheses, and it's times dx. What is my ultimate goal here? To find dy dx. So this is where we want to kind of manipulate things to find dy dx. I already have dy on the left, yes? How do I get the dx over there? We're going to divide it. What about this 1 divided by y?
We can multiply both sides by y.
We're going to multiply the y over to the right. So dy stayed. I divided dx to the left. I'm going to multiply the y to the other side. So I have y times what's in the parentheses there. 2 over x minus 12 over 3x plus 2. And we are one step from being done. we want the derivative of y with respect to x. So my answer should all be in terms of x. And we have a y thrown into the mix. Now, the thing is, it's just a plain old y. What do we know about y?
It equals x squared over 3x plus 2.
Y was originally defined as our original function of the dy, or x squared over 3x plus 2 to the fourth. So basically, to finish your answer, to find this dy dx that we're talking about, you're going to take the value of y and replace it in the equation. So x squared over 3x plus 2 to the fourth, and then still times 2 over x minus 12 over 3x plus 2. If you can see it there in the mess of everything else, that is your final answer.
Just when we got to the part with the y, I was thinking like, well, that can't be it, because if the big quotient rule couldn't clean up that much, we got that.
Now you've got a mess, yes. And keep in mind, if you had actually done this problem with quotient rule, is this the answer, how your answer would look like? No, because our quotient rule would come up as one big fraction. And so this isn't exactly how our answer would look, but it would be equivalent. Okay. My opinion is it's not too bad, but there's a lot of writing.
In between steps.
Huh?
There's a lot of in between steps.
There are a lot of in between steps. Now, as you become more comfortable with them, there are definitely some of these in between steps you can knock out. I wasn't knocking anything out the first time through, because I don't want you guys to look at me like, whoa, how'd we jump? How did this jump happen? Okay, we ready to try example 2? Do we remember the first step? Take the natural log of both sides. So I'm going to rewrite this as the natural log of y equals the natural log of x cubed square root of x squared plus 1 over x plus 2 to the 6th. And you may get to the point where you skip that first step I just wrote out. After we take the natural log of both sides, what is my next step?
Split it up.
Split it all up, right? If you see multiplication, we're going to rewrite it as 2 logs being added. If you see division, we're going to write it as 2 logs being subtracted. So natural log of y equals, what's the first one you did?
Split the top. Because that's like x to the third and then square.
Right.
X squared.
So realize there's multiplication up top, yes? So the first piece I can grab is natural log of x cubed. Now, if I'm really combining steps, what about the natural log of x cubed?
3.
Can I take that 3 out front and make it 3 natural log of x? Could you do that in the next step just as well? Yes, I'm just realizing I'm going to run out of room on this bin cube real quick. I should have made this a screen of its own. Okay, so that piece right there is natural log of x cubed. Then it's times, so I'm going to say plus. Now I have the natural log of this square root. A square root is really something raised to the 1/2 power. So if I take the 1/2 out front, it's 1/2 natural log of x squared plus 1. So that was me taking the square root, changing it to 1/2, putting my power out front. The next part is division, so we're going to be subtracting. It's natural log of x plus 2 to the 6th.
So 6 ln x plus 2.
So I can take my 6 out front and say 6 natural log of x plus 2. Some of you guys are going to get fancy enough, and you're just going to, the step I just wrote, that's going to be your very first step.
That's what I started.
So, and I can see that. Okay. Are we okay with what I've written here, or did I skip too much? I don't know. And now that I'm thinking about this, I'm going to have half the class listen to this on recording.
I sent Abby the notes yesterday.
Okay.
I don't know why she wanted mine, but I sent her the pages of the book yesterday.
Well, I say it'd probably be easier to look at the notes rather than listen to a recording where they're at. So, okay. Are you okay with what we have here? Okay.
I did the other stuff too, so it's kind of like
Okay.
back and forth.
But it matches up, right?
Yeah.
Okay. And that's fine. Again, however many or few steps as we want. After we have it all separated out, we've used that power rule and put the powers out front. Now we're going to take the derivative of everything, right? The derivative of natural log of y. One over y dy. Every time, guys. Every time. Derivative of 3 natural log of x.
3 over x dx.
Okay. So the 1 over x times the 3 makes it 3 over x dx. Plus
2x over 2 times x squared plus 1.
So do you have a fraction within a fraction there?
Well, I just took the 1/2. So I did the derivative of that, which was like 2. It was 2x over x squared plus 1.
Okay.
And then I just multiplied it by 1/2. You just put a 2 on the bottom.
Yeah.
That's what I did.
Okay. It's not how it sounded, but so if we just think the derivative of natural log of x squared plus 1, that's 1 over x squared plus 1, yes? Times the derivative of x squared plus 1 is 2x. But what did we also have out front? The 1/2, which the 1/2 is just like multiplying by 2 in the denominator. What am I going to be able to clean up next step?
Distribute.
I wouldn't distribute the 2.
Cancels the 2.
I would say that 2 and that 2 will cancel is what I would say. And don't forget, I almost did the dx. Minus derivative of natural log of x plus 2 is 1 over x plus 2 times the 6 that's out front times dx. Okay. Officially, I would clean up that right side and factor out all your dx's. So I'm going to say 1 over y dy. And let's see, I'm going to have 3 over x plus, if I cancel those 2's, I'm going to say it's x over x squared plus 1 minus 6 over x plus 2 in my parentheses, and that's all times dx. Okay, my goal is to solve for dy dx. So I'm going to keep this dy where it is. I'm going to divide the dx over. These 3 terms in the parentheses on the right are going to stay. And since it's 1 divided by y, I'm going to multiply by y. Now, I can do this 2 different ways. I could go ahead and write out y times this and then rewrite it with y. Or how fancy are we? Can we go ahead and put y in? I don't know. I might be asking too much here. But the idea is this is supposed to be y times all that stuff in parentheses. Well, y is x cubed square root of x squared plus 1 over x plus 2 to the 6th. That is y. And then it's times everything we had in parentheses. 3 over x plus x over x squared plus 1 minus 6 over x plus 2. Lots of little steps, making one big thing.
I don't remember when math answers.
Math answers were a number? What?
Just like a nice little like 4. No.
So Natalie at dinner last night, she's 6th grade. She says, yesterday we solved 1-step equations, and today we are solving 2-step equations. She goes, what did she say? She goes, what comes after 2-step equations? And I said after that it's just multi-step equations and then variables on both sides. She kind of looks at me, she goes, so does that mean there'll be an x in the answer? Meaning on the answer side of the, like, so in her mind it's still the equation equals this one number. And so I was like, I guess so. Like, you know, I'm talking to a 6th grader here. I have to.
Nah, you should start teaching her calculus now, so by the time she gets here, she's just whiffing it.
Yeah, no, that would not go over well.
Traumatize her.
Okay, example 3. This is the one that I look at and I'm like, oh my gosh, I could not do that any other way. Like, I could not use our other methods for this one. No way, no how. So, can we go ahead and take the natural log of both sides and break it into all the pieces? Did that go over okay last time? I may have to touch base with some of the people that aren't here. That may be the tricky part, but. Okay, it's a y, the natural log of y. Natural log of y. Then if I break this into pieces, the natural log of the square root of 3x plus 2. So if I take the power of 1/2 out front, it's 1/2 natural log of 3x plus 2. Then it's times the x cubed plus 1 to the 4th. So I'm going to say plus. I'm going to bring my power out front. So it's 4 times the natural log of x cubed plus 1. There's another times portion. So I'm going to say plus, bringing the power out front. So it's 2 times the natural log of 5x minus 3. Then there's division. So now I'm going to say minus, take that power out front, so 5 times the natural log of x cubed minus 2. Are you guys taking the derivatives without me? Okay, that's fine. As long as I'm not going too fast, it's all good. Okay, the derivative of natural log of y. 1 over y dy. Derivative of 1/2 natural log of 3x plus 2.
3 over 2 times 3x plus 2.
Okay, so I'm going to start by saying 1 over 3x plus 2 times the derivative of 3x plus 2 puts a 3 on top. Then we had that 1/2 out front, which means there's a denominator of 2. Okay. Plus 4 times the natural log, so it's going to be a 4 on top. Derivative of natural log of x cubed plus 1, 1 over x cubed plus 1
Times 3x squared.
times the derivative of x cubed plus 1, which is 3x squared. Plus 2 times, so the 2's on top, natural log of 5x minus 3, so its derivative is 1 over, gosh darn it. Okay, well, I'm going to adjust. What am I forgetting on every single term?
dx.
dx. So what could I just do?
Now, see, this is I was going to ask you this. I started where I just put the dy on the left, and then I just put the dx at the end of it all. Can I start that way?
Yep. That's what I'm going to be doing next because I don't want to go in and try and throw the dx's in. And actually, as I look at my notes, you can just write the dx at the end. Okay? Just realize where it is so we get it all set up right at the end. But, okay. So, sorry, just had that realization mid-problem. So derivative of natural log 5x minus 3 is 1 over 5x minus 3 times the derivative of 5x minus 3, which is times 5 times the 2 is already there, minus, we have 5 on top, derivative of natural log of x cubed minus 2 is 1 over x cubed minus 2, times the derivative of x cubed minus 2, which is 3x squared. All four fractions on the right should have said times dx. But your teacher is forgetful and forgot. So, to rectify my mistake, I didn't forget. I meant to do this all along. I just put a times dx at the end. And you can do that. That is perfectly fine because they're all x terms. Okay. I can finish this in one more step if you want. I'm going to keep the dy where it is. I'm going to divide over the dx, so it's divided by dx, right? Equals. Now, what about that 1 divided by y? I'm going to multiply that y to the right. So you can either write y here and then rewrite the whole problem later, or what is y?
The big long equation.
Okay, the original problem, right? Square root of 3x plus 2 times x cubed plus 1 to the 4th times 5x minus 3 to the 2nd all over x cubed minus 2 to the 5th. So that right there, what I just wrote in, that is y. Okay? And then it's times everything in the parentheses. 3 over, and I did make it 6x plus 4 on this next piece, so I did kind of clean it up. You wouldn't have to. So I said 3 over 6x plus 4 plus 12x squared over x cubed plus 1 plus 10 over 5x minus 3 minus 15x squared over x cubed minus 2. Skip as few or as many steps as you prefer, right? Are we okay with what I've been doing? I will be curious to hear from Ethan, Abby, and Maddie about how this lesson goes over without being in class. Okay, example 5. Y equals x to the power of x. Find dy dx, given that the domain of the function is a set of all positive real numbers.
Is that thing where it says all positive real numbers, is that just hinting at us to use logarithmic differentiation, or whatever it's called?
Probably. Okay, so take the log of both sides. So the natural log of y is ln y. Take the log of the right. Natural log of x to the x.
So x.
So if you go ahead and move that power out front, it's x ln x. Okay. Now we're ready to differentiate. What is the derivative of natural log of y? 1 over y times dy. What is the derivative of x ln x?
X x over x plus ln x.
Okay, yes, I think. What do we have to do here?
Product rule.
Realize x is something I can take the derivative of, yes? ln x is something I can take the derivative of. So this is a product rule. Okay, derivative of one, keep the other, plus, and then flip-flop it. And so you have to realize, I was trying to process if yours was equivalent, but I think it is. So if we do this, the derivative of x is 1 times the natural log of x. So that's the derivative of the first, keep the second. Plus, now I'm going to keep the x. What's the derivative of natural log of x? 1 over x. Now, these are all x's on the right, so I'm going to say times dx. I would go ahead and clean up. 1 over y dy is equal to natural log of x plus, what is x times 1 over x? 1?
It's definitely something like this.
Oh, were they leading you in last night?
Yeah, I remember.
Okay.
There's something like that, or something that was very similar.
Okay. And at this point, you're ready to solve for dy dx. I'm going to keep the dy where it is. I'm going to divide the dx over, right? If it's 1 divided by y, I'm going to say times y. I'll fill it in a moment. You can go ahead and fill it in if you want. And then times ln x plus 1. Except we don't want to leave a y there, right? So dy dx is, what is y? X to the x. So we're going to say x to the x times natural log of x plus 1. Natural log of x plus 1. Got one more. Similar to what we just did. So basically I'm giving you a way to take the derivatives when you have an x in the base and an x in the power, if you'll notice.
Which is something we previously couldn't do without a calculator, right?
Correct. That's something that's not a derivative rule we had. Okay, so this is y equals x to the x cubed plus 4. Find dy dx. So take the log of both sides. Natural log of y is equal to natural log of x to the x cubed plus 4. If you go ahead and put that power out front, it's x cubed plus 4 times the natural log of x. Notice I put that x cubed plus 4 into parentheses. We take the derivative of both sides. The derivative of natural log of y is 1 over y dy. What about the right? We've got x cubed plus 4. We've got natural log of x. Those are two different functions. We can take the derivative of both, so we're going to use our product rule. Derivative of x cubed plus 4, 3x squared, times the ln x we're keeping. Plus, this time I'm keeping the x cubed plus 4, times the derivative of natural log of x, so times 1 over x. Officially, this side is all times dx. I just put a big old parentheses and put the dx at the end. I did distribute that 1 over x in at the end, just as part of some cleanup. So I have 1 over y dy is equal to 3x squared ln x plus, and if I distribute this 1 over x, 1 over x times x cubed just becomes x squared plus 1 over x times 4, 4 over x. Okay. And again, I mean, could you leave it even messier and leave it like the original one? Sure. Keep the dy. Divide dx over to the left. If it's 1 divided by y, we're going to multiply by y. If I go ahead and put y in, it's x to the x cubed plus 4 times 3x squared ln x plus x squared plus 4 over x. And you're good. And again, just reminding you, this piece right here was, since it was 1 divided by y, we multiplied by y there. Number 4 becomes 8 from 77. Is your substitution of the day. Okay.